Hello, everyone. I hope everyone is doing great during this pandemic. Today, I'm here to present my master's level project, which is titled as Autonomous Vehicle Using Deep Learning and Edge Computing. So to start with the problem statement, the main problem with the current level of object detection and the current level of computation, which is required to do that in the autonomous vehicle is huge. So previously, what used to be done as to the process which was followed was to collect the data and process all the data over the cloud, and then send the signals or the data commands, the parameters to the car to navigate successfully. But the problem with this approach is that the cloud computing takes a lot of time to relay the information, because as we know that the data is collected from a vehicle, or we can say from a car, and then that data is sent remotely over the network to a cloud, and then cloud feeds that data to state of the art algorithms, and then sends the parameters like the output of the algorithm to the car to navigate successfully in a real-time scenario. But there are two main key problems with this approach. The first problem is that there's a bandwidth cost, like someone has to pay for the data transfer. And secondly, as we know that autonomous cars have number of sensors, so as the number of the sensors and the complexity of these sensors increases, the amount of data which needs to be processed at the real time also increases. So to remedy this problem, an alternative to cloud computing is edge computing. So when we say edge computing, it does the edge computing does the same task which a cloud does, but it removes all the problems which are associated with transferring the data over the cloud and then processing everything in real time. So to avoid the phenomena of low latency and the time delays in real-time navigation or real-time object detection, because as we know, object detection or lane detection, even though there are not even though they are like terms, but it can result in life and death situation when a car is dependent on a remote server to compute its data and send um, the required parameters to stop whenever there's a person or a dog in front of the car, or any robot, you say, in an environment or like an industry situation. So as an introduction, as I said previously, that lot of acc- lot of accidents on the road are caused because of the negligence or people not following the rules. So the Insurance Institute of Highway Safety did a survey a couple of years ago where a simple situation such as running a red light has injured 132,000 people, and there have been around 900 deaths in just the year 2017 in the US. So imagine what would that number be in the whole world. So definitely it is a problem which needs to be addressed, and it is addressed by autonomous vehicles, by like including different features like autonomous lane navigation, lane assisting, adaptive cruise control. But there are many limitations to these systems, and these limitations are avoided by companies like Tesla, Waymo, Ford, and many other companies. But the approach that is being implemented by the other companies than the Tesla are by using a lot of sensors. So when we use a lot of sensors, we need to have a processing unit which can compute all this data, because if we consider sensor as like a camera, LiDAR, radars, these sensors generate huge amount of data, like huge amount of data. And to process all this data and to make sense out of it is the important thing. And when you have such amount of data coming in such a rapid pace when a car is going at 60 or 100 miles per hour, even a problem of a millisecond can result into a huge accident or any casualty, we can say. So what I am proposing is where the computation of data can be done at the edge. So that is when the concept edge computing comes into the picture. So with edge computing, all the computation which is supposed to be done on cloud is done on the edge node itself. So in my project, the edge node I have used is a Google's Coral TPU. When I bought it, it was in beta process, but they now have released it. There has been limited amount of work done on it, but I see the potential of using the edge nodes to do all the computations in the future for a self-driving car. So to demonstrate that, what I have done is I have built a physical hardware car using SunFounder's um, PyCar kit. And as you can see on the slide, the kit has a controller unit, um, which is a Raspberry Pi, which controls all the computation. And there's a camera on the car mounted in front of the car. So it is just like a miniature version of an autonomous car or any robot. And then there are three servos in total, two servos, one servo each on the rear wheel, and a servo to control the front wheels, like the turning of the front wheels. So there are in total three servos. So basically what it demonstrates is the working of a real life robot or a real life car. But on the addition, so this kit comes disassembled. We have to assemble the kit, and then all the functioning of the components, the servos have to be tested. So in my zip folder, which I have provided, I have already given a code to configure these servos, because these servos are configured. These servos cannot be configured manually. They have to be configured with the software, and they have to be at a specific angle so that they won't damage. So moving forward with that, um, the approach which I followed was to do everything from scratch, build the car from scratch, and then implement OpenCV techniques for lane detection and navigation, and then object detection to do all the necessary object detection and passing the parameters to the car to stop in time. But all the computation, the problem with right here is that Raspberry Pi is computationally insufficient to do real-time computation. So that is when the concept of edge computing comes into a picture. So Google has provided a USB accelerator, which we can also call as edge TPU in this scenario, which can do a lot of computations, and it is comparatively less than half the size of the Raspberry Pi. So with that, what happens is we can offload all the computation tasks to the TPU, and then the CPU, or we can say a microcontroller, can be used to do all the inferencing. So with this, what happens is all the data which we need to compute gets computed at the edge node. We don't have to send data remotely anywhere to be computed. And This can be replicated in real life robots or in the industry level or at a bigger level for a self-driving car. But it has a long way to go ahead. Why do I say that? I'll explain to you more in the later. So so these are the specifications for the Raspberry Pi I have used. I have used Raspberry Pi 4B. The SSD card is class 10, which gives the maximum speed and is of 64 GB. Um, there's no need of using such a big SD card, but as the model, like the deep learning model grows, the model becomes more in the size in terms of MB to GB, so that is why it's a bigger SD card. And yeah, the Google Edge TPU, which only right now works in Linux system as it's in beta stage, it can do 4 trillion operations per second. So all the machine learning and the deep learning computations can be offloaded to the core TPU. In the presentation slide, you can see a device which has name written as Coral on it. That's the Edge TPU compared to the Raspberry Pi. As we can see, it's not even a half the size of the Pi. And it can already do 4 trillion operations per second. And any state of the art computer vision or deep learning model can be deployed over this Edge TPU at 400 frames per second. 400 frames per second is a lot, but as the amount of sensors and as the amount of data grows, the FPS will naturally come down to, we can say, around 30 to 60 frames per second. Because for autonomous navigations, a lot of pre-processing has to be done on the images, which ends up taking a lot of computation power and in terms reduces the frames per second from 400 FPS to 30 to 60, depending on the model which we are running and the size of the model. For now, Edge TPU, Coral Edge TPU only supports TensorFlow Lite, but Google is already working on providing more support for PyTorch and Cafe and all rest of the um, deep learning architectures. So in the slide, we can see that the dimensions are 65 mm into 30 mm. That is like, if you take your 2 fingers, it's that size. So the cost of the HTPU as of November when I bought it was $75. And yeah, so so the so the approach for the project, like when I started researching into the project, the things which I found out from my study, you can see it as a background study, is that many advanced sensors are being used for autonomous navigation, like autonomous driving. Sensors like cameras, radars, and many other computer vision techniques are also used, like implemented on with these sensors, and then autonomous driving um, is successfully performed in any given environment. So it is a combination of computer vision techniques, deep learning models which can detect stuff, and also inferencing the data coming from the sensors, which is also called as sensor fusion, where when we have number of different sensors and we integrate that data together and make sense out of it to provide real-time commands to a car or a robot in any given environment. So previously, as I said earlier, that the data, whenever the data used to be collected, it used to be sent over the cloud for processing, but we are trying to achieve it at the edge by using Edge TPU. So one upper side of cloud computing is that it can handle large amount of data. It is not limited by its hardware. In a sense, it is, but if you have a huge data storage, then at that moment you won't have any problem with the limitations. But as the size of the edge node increases, I believe that we'll have mm, a huge capability of computing huge amount of data. So it can be used to operate vehicles and do all the computation at the edge. So, but the upside of edge computing, even though it's limited by its hardware, but the upside is the time efficiency is really, really good because all the data directly gets transferred to the node because the edge node is physically connected to the microcontroller. So data transfer rate is really low. Transfer rate is really fast. Latency is really low. And then the robot or the functions of the robot doesn't have to depend on any remote network or any network to send and receive the data to make those decisions. So here, moving forward, that here is the architecture for autonomous lane navigation. So we can see here in the architecture, the first thing which is needed to be done is to capture an image. So while implementing the project, I had to construct a demo road. As you can see in the picture, it is a representation of a real life road, has a black surface and it has white lines on both sides of the car. To capture this, why do we need to capture this image is to figure out um, the necessary parameters which we need to detect those lines. Because some part of OpenCV depends on what color are you trying to detect, what edges are you trying to detect, and then what is the region of interest. So it won't be computing the whole image. So in our scenario, in our um, for our purpose, the only thing which we need to consider is the road which is right in front of the car. So in the diagram over here, that's the architecture of lane navigation. The algorithm starts with capturing an image. So once this image is captured, we can apply a bunch of OpenCV techniques. I have also submitted an IPNYB file. The pre-processing and tuning all the hyperparameter, I did it on Google Colab to just save time and try multiple things instead of doing it on Raspberry Pi. And then I took that code and then merged it with my Raspberry Pi.py file. I'll explain that on that more later. So right now, as we consider the architecture, um, once we capture the image, so the video is just a bunch of images. So once we isolate a single frame, all the pre-processing has to be done on each and every frame or each and every image. So imagine if a video has 100 images, the video is only like 1 second long. So we can see that it is like we have 100 frames for 1 second of the video. So when we have 100 frames, these pre-processing techniques have to be implemented on each and every frame to get those accurate results. So the higher the frame rate, the lower the performance. But if we have a better performing algorithm, we'll have higher performance with better lane detection. So Once we capture the image, the other steps which I perform and which are generally performed are isolating a region of interest, which saves a lot of computation power as you only have to process the lean lines in front of the car and not the rest of the video. So once the pre-processing is done, various edge detection algorithms are implemented on a like use line transformation, edge candy detection. There's adaptive thresholding in OpenCV. There are a bunch of edge detection algorithms which can be implemented once we find the region of interest and then generate those edges. These whole processes are repeated on each and every single image, which ends up taking a lot of computation power. And that is why we need a lot of computation power, is to apply these OpenCV techniques on each and every image. So once we're done with that, over here we can see on the right hand side, I have used edge candy detection where it perfectly detects the lines in front of the car. And once it detects the line, we can then isolate the region, which is also called as region of interest. In our case, it's only the half of the bottom image. And then once we have isolated that particular part, we can mask that isolated region and the detected edges on our original captured image. So our original captured image was this one. And then once we mask those detected edges on the original image, we'll get perfectly detected lines on the both side of the car. And with additional processing, we can fill out the gaps between the lines and then get a solid line on both sides of the car. In my case, I have given it a green color, so you can see there's a green color line on both sides of the lane. And then the, the center line is to predict or to determine the steering angle which the car is supposed to take once the lane starts curving or any other thing like that. So we can see over here when the car is going in a straight direction, the lines are in straightly aligned with the actual lane line, and then at the curve, the line tilts towards the left as we have a left turn. With the object detection, um, for edge detection right now, for at the moment, um, edge TPU can only um, support TF-like format of the model. So if we have a model which is in any other format like .pickle, .pb, .onnx, or any other format, these models have to be converted into a quantized format. And I have also provided a link in my report so that um, it is a web service provided by Google Coral.ai team where you can put in your original pre-trained model and it gets converted into the .tf file and the quantized format which is needed for the HTPU. Because why it is needed is to like the pre-trained models which we have are heavily dependent on having high computation. So when our machine has like a GPU or has CUDA capabilities, no matter what our model size is, we'll get a good result with higher frames per second. So generally speaking, we'll have a greater computational power. But with the TPU, comparatively, as the TPU size is really small, we'll have limitation um, when compared to the big GPU or multiple GPUs or parallel computing. So that is why it has to be converted in a specific format. So with that, once that is converted in a specific format, we can integrate both of our approaches for The first one was for lane navigation. Over here, we can see that when the object is far enough, the lane navigation system is trying to navigate through the lane, and once it detects the object, once the object is near enough to the car, I detect. So for here, I have represented a person, a pedestrian, in terms of the bottle, um, for demonstration purposes only. You can place a real human being or a figure of a human being, and it will detect a person. And once it detects the person, the car stops. And we'll also see this in the demonstration. Once the car stops, the car will continuously keep on detecting the object which is right in front of the car. And once the person or the object moves far away, like moves far enough from the car, then it will start moving again. We can see the working of this in the demonstration. So Raspberry Pi in itself is not highly efficient and not capable of computing so much of data for object detection with um, the frame rate I got was 38 frames per second, which is good enough for real-time computing. 32 frames per second, which is good enough to detect objects in time and then compute the data of the object or the coordinates of their object, and then send it over to the controllers or the servers of the car to stop in time. So the activities which were performed um, while this project was being developed, um, I will try to go as deep as possible because a lot of technologies have to be integrated together, um, starting with the specific version of the which is a Linux variant called Noobs Raspbian. So what it does is it already has all the necessary libraries and required drivers which are needed to be installed in the Raspberry Pi for um, the interaction with the servers or any other hardware which is attached to the Raspberry Pi. While installing these operating systems, a person can face a number of challenges as um, the uh, monitor or the HDMI cable won't get recognized because there are number of configurations in the config file of the operating system itself, which needs to be changed and specifically defined. I have also mentioned this in the report, so the necessary changes can be made. As Raspberry Pi is power efficient, connecting an external hardware such as a computer for as a monitor, a TV as a monitor, it will consume a bit amount of power. So that is why the config file has to be changed. And then um, installing as soon as the USB camera is plugged in, because Noob's Raspbian operating system has a lot of drivers pre-installed. You don't have to specifically install a driver. It detects the USB camera automatically and installs all the necessary files. Along with that, CNC VC viewer is also supposed to be installed. So because the problem is we cannot keep the monitor or the TV connected all the time, as I mentioned earlier that it will end up consuming a lot of power. So we need to establish a remote connection from our computer to the Raspberry Pi's operating system. So that is where we can use the VNC application. The procedures of installing the server of the application in the Raspberry Pi is mentioned in the report. And then there's a general applications for any operating system. Like personally, I'm using Mac OS, so there's a Windows version as well too. And then you can just type in the IP address of the Raspberry Pi, provided that Raspberry Pi has a Wi-Fi driver and is connected to the Wi-Fi network. It will establish a connection to the Raspberry Pi operating system from our computer. The third thing, which was really important, was to assemble the PyCard kit. So the Sunfounder delivers the kit in various bits and pieces. The manual is also provided with along it. Well, you can refer, like I referred the manual a lot of times while assembling the card, because each and every component, the PWM module, and all the necessary hardware needs to be go into the right place and connected accordingly, or you can end up damaging the uh, hardware components of the card. After setting up everything, Sunfounder has also provided an open version Python API, which can be downloaded from the GitHub. Just type in Sunfounder PyCard. Um, it will direct you to the repo. Just fork the repo in the um, Raspberry Pi, and we are good to go. We don't need to hard code each and every line or each and every thing to make our car, to like perform our car. We can directly do it by inputting some lines from the API. Um, Moving forward with that, once everything is done, you'll have to install OpenCV libraries for the processing of the images. Once the OpenCV library, it also has its own challenges. I've also mentioned those challenges and how to overcome it in the report in detail. A TensorFlow library has to be installed for CPU and also as TPU. As you might know, it also has a lot of challenges. I have mentioned those challenges in the report and how to overcome it. Then the algorithm, which I explained earlier, needs to be performed on the Raspberry Pi using OpenCV. Um, the code is provided in the zip folder. Moving forward with that, a deep learning model, pre-trained deep learning model, like quantized deep learning, a specific type of model has to be saved on Raspberry Pi so that it can um, make use of that saved model in runtime for all the processing of the images, or we can say to navigate our car. And some additional features are also I've included in the code. Um, I've also provided comments along the code for how to initialize the Edge TPU engine and how to inference the object detection model with using Edge TPU computation power. And in the end, if everything is working properly, everything is installed, the hardware is connected properly, and everything is working, the software is installed with no errors, then basically we can have the code which I provided. It's just copy paste the code and follow the how to run the project guide, and then everything would start running. The development environment I used was as I said earlier, it was Raspberry Pi, which has 4 GB of RAM. Um, then a Google Edge TPU, which can do 4 trillion computations per second. Then I had to keep a lot of batteries in stock, as they used to run out in 10 or 15 minutes. The SD card, as I explained earlier, is 64 GB. The camera, yeah, the camera was a wide angle, like a fisheye, 170 degree. It has a field of vision of 170 degree. Um, because the more the amount of environment a car can see, the better it can predict the objects which can gradually come into its path, or it can start detecting from far enough. And then the PyCar came with all the servos and the PWM drivers and a lot of other stuff which needs to be. So referring the manual is really important. Was important for me, and then is also important moving forward. Um, the extra components here, the miniature traffic sign and pedestrians, as we know, due to the coronavirus, I wasn't able to get it delivered in time. I've been waiting on them for like more than a month. It's been like around 1.5 months, but due to pandemic, I wasn't able to get those components. But that is why I placed a bottle to represent a person, um, and we can see it's working in the demonstration part. There has to be I had to install a lot of software, um, which were compatible to a specific version. So the specific versions are also provided in the report, in the implementation and installation sections, because some versions of OpenCV aren't compatible with TensorFlow, Lite, or HTPU. So these specific versions are needed to be kept in mind moving forward, as even because even if one library doesn't work, the whole car won't function. The model which I used was the CNN's MobileNet SSD model, which was in a specific format. I've also provided a link to how to consider a model, how to convert it into a specific format. And then Google Colab was also used to tune the hyperparameters for lane detection and determining the edge detection algorithms, like which algorithm works perfectly for my particular situation. Um, then other applications such as label image was used for annotating the data. VLVNC viewer is the application used for remote viewing purpose. A camera app, which is Cheese, was used to check if the camera is successfully installed. And then TPU model web compiler was used to convert the pre-trained model into a specific quantized format for HTTP. So these are my references, and the deliverables for the project will be a deep learning model, a specific model which is supported by the HTPU is included in the zip folder. The presentation and demonstration video will be up on YouTube. The project source codes basically has all the necessary files, such as CapCV, which can be used to capture a single frame of image for playing around, detecting lines for edge detection. Then server.py can be used to configure the servos, and then project.ipnyb file was used to do all the pre-processing. And um, we can see in details how the pre-processing was done on each and every line with Google Colab. And then the Pi folder has the all necessary files for the uh, working of this project. But the working of this project is hardly depends um, on the integrations of the hardware and the software which were used. So I would recommend to use the specific versions of the software and specific um, Sun Founders PyCard kit to integrate everything and implement it successfully. And I've also provided a detailed report which has all the necessary information, the implementation, the specific versions, how I implemented it, what were the things taken into consideration while implementing, what was the challenges I faced, um, and what was my background study about this particular topic, and what are my uh, recommendation to uh, for the betterment of this project. So yeah. Thank you very much. And we'll start the demonstration.